Okay, so the title of this is Brain-like Object Recognition with High-Performing Shallow Recurrent ANNs. And I really want to start by acknowledging that this is not just my work, this is really a collaboration with many wonderful people. Most of all, I want to highlight Jonas Kubilius, who's really, especially for the two topics that I'm going to talk about, has contributed a large share of the work as well. And all of this is under the supervision of Jim DeCarlo. All right, so our goal in the lab is to find an accurate model of the primate ventral visual stream. Why do we do this? I think there are three primary reasons. So one of it is that an accurate model will give us a mechanistic understanding of how human or primate object recognition works. It might inform the next generation of vision intelligence algorithms. And finally, probably a couple of years down the line, there might be some clinical applications that we can use these accurate models for. And what I'm going to talk about today are really two steps in that direction. So one, Bud has already alluded to this, is a platform called BrainScore that we use to compare between the brain and models of the brain. And the other one is one such model that is a bit better, called CORnet-S, that tries to model the brain more accurately and does pretty well on some interesting tasks. All right, so to give you a brief background on how to think about object recognition in the brain. So there are four cognitive areas that are primarily involved in core object recognition. They're called V1, V2, V4, and IT. And the idea is roughly that features, as an input comes in, as an image comes in, features are transformed in a hierarchical manner. So V1 processes it first, and eventually features end up in IT. And out of IT, sort of if you want to think in machine learning terms, it's something like the last layer before the classifier. So from there, you can perform different tasks. You can answer questions about object identity, object size, rotation, and whatnot. So when we want to compare models of the primate ventral stream to the brain, then the two primary data we use so far are one, behavior data, and second, neural data. So those together make up the suite of BrainScore benchmarks. And you can think of this as behavior data is really the outputs of the system. And neural data are the internal processing steps. So these are what we record with electrodes mostly. So I'm going to start with one behavior to give you a sense of what this looks like. And this is really the primary behavior we focus on. This is the object recognition behavior. And so the task is something like this. If you were a subject in our experiments, you would see an image like this one for only a very brief time, usually 100 milliseconds. And then you'd have to decide which of the two objects matches the image most closely. This is pretty simple. I hope you would all see the puck on the left. But as we speed this up and as we show objects in more difficult configurations, you can probably imagine how this can get pretty difficult. So we show this to humans on mTrick, as well as monkeys, but for all of these different tasks, so for instance, discriminating between a camel and a truck, you can fill this matrix that tells us how difficult it is to categorize one over the other. So for instance, categorizing images of dog against the distractor of a fork is pretty easy. Whereas the person always has trouble with categorizing the image of an elephant versus that of a rhino. So red here means that certain tasks are more difficult. Green means that they're more easy. So you can see that there's a pretty diverse pattern. Humans are on average really good at this, but there are certainly tasks where it becomes more difficult based on the difficulty of the image as well as the task itself. So the same thing can now be done on the model. We can run the same images and the same kind of discrimination tasks on a model and obtain a behavior matrix. And what we basically test for is how closely the model behavior matches the human behavior. So does the model not just get the same things right, but also make the same mistakes as humans make? And another nice property of this task setup is that it can be pretty easily done by our macaque evolutionary neighbors as well. So this is a sample video of macaques in the homepage performing this task. They see the same images that you just saw, and you can also see the binary discrimination task. They get rewarded with choose water if they get it right and the green screen, and if they get it wrong, they get a timeout and this black screen. So they're pretty fast and pretty good at this. This is the main task they're trained on, so they might be better than most of us humans if we're not trained on it. But yeah, this is all to say that they can do this task really well. And what this now allows us to do is that we can implant electrodes in different parts of cortex, and in response to these images, we can record what the neural activity is as these images get processed by the brain. So you can again think of this as one vector per image, where each element in the vector is the neural activity of a particular neuron in response to that image. So overall, what you get at the end is a matrix of images times neurons. And again, each element in the matrix is how active is a particular neuron to this particular image. I think someone that's unmuted. I hear myself.
Okay. Can you put your legs on like that?
Louise, I think you're unmuted. If you want to mute yourself. Right. So we can again do the same thing in the model now, where we originally record from the model, which just means we extract the activations at different parts of the network. And then we again ask, how closely does the model match the brain? And here we ask, how closely do the recordings or the internals of the model match the recordings that we get from non-human primates? So to give a bit more detail on this, what we typically do here is that we split these two matrices in a 90-10% train test split, and we use 90% of the images and the corresponding model activations to fit a linear matrix or a regression to the brain recordings. And then using those found weights on the held out 10%, we try to predict what the brain recordings for those 10% held out images will be. And then we linearly correlate how well we've predicted all of that. And we do all of that in a cross-validated manner, and that gives us a score. So it's really like, is the linear transformation from model activity to brain activity? And how good is that? That is what is being tested here. Yeah, so trying to put all of this in a clear picture, we do show images to the brain primarily, then we record not just from one brain area, but from different brain areas. These are data sets now obtained both from our lab as well as collaborating labs of Tony Mofshan. And we also test for primate behavior. And all of this is quantified in these brain score benchmarks. So like the modeler will not have to worry about how exactly all of this works. They basically just submit a model. Asif, I think you're unmuted. Yeah, so as a modeler, you would submit a model, and then these benchmarks directly tell you, without you having to do much else, how good you match that. How that works is starting from base models. So these are the typical machine learning models, something like ResNet, for instance. We convert them into what we call a brain model. So those are models that make commitments to regions in the brain as well as spike rates and whatnot. And then we test using the methodology I described before, how closely do the neurons in the model match those in the brain, and how closely does the model behavior match that observed in humans. Okay, so now when we actually run these models, it can go something like this. So again, I told you there are, let's say, 5 benchmarks ranging from early visual cortex V1 to higher level visual cortex RT and behavior. So when we now test a model like AlexNet, it gets a certain score. And yeah, we've tested over 100 or hundreds of models at this point. And you can see that there's a pretty wide scatter of how well these different models perform on these different benchmarks. We then pack all of this into a website called brainscore.org, which I encourage you to visit. So this always has the up-to-date model ranking, and we compare all those models in a unified manner on all these benchmarks. So it's a fair comparison. And our community, like not just our lab, but also the wider computational neuroscience community, is adding more and more benchmarks so that we can evaluate all the available models. So for instance, the benchmarks that Thiago talked about in a couple hours ago, those will be added very soon as to add to those V1 benchmarks. So whatever data we come up with or whatever benchmarks we come up with, those are always added to this website. Okay. Now, one of the major findings that came out of this study in the very beginning already was that if you plot the ImageNet performance of certain models, so here in the x-axis ranging from very bad to pretty good ImageNet performance, top 1 accuracy, and you plot that against the brain score, here's the mean of V4-18 behavioral scores, then you do find a pretty strong correlation. So generally models that perform better at the ImageNet categorization task are also models that more closely match the primate visual stream. Yeah, so overall models that are better ImageNet are also more brain-like. And at the time when we did this, we found that the most brain-like models that were not built for the brain at all, always the story of like, it did not have to be that machine learning models tend to be good models of the brain, but it happened to be that especially ResNet and DenseNet families are pretty good models of primate visual processing. But I also want to point out that still there's a huge gap So there's a lot of work to be done in building more brain-like models of vision. Yeah, so to give an interim summary of this first part about BrainScore, so this is a platform that organizes brain measurements into quantitative benchmarks. BrainScore embraces all models. It does not care about how complex the models might be. There's a bit of a break from classic neuroscience where there's more of a focus on simple and easily explainable models. Here, we only focus on how well the model matches the brain, regardless of simplicity or lack thereof. And finally, it shows that some artificial neural networks are first approximations of the brain's ventral visual stream, but also that there is quite a long way to go. So in this next part, I want to talk about some ideas for how we can get closer to matching the ventral stream. So there's many problems, but I'm going to focus on two of them. And that is, if you consider a ResNet 101, for instance, where there's over 100 layers, and you try to map that onto 4 cortical regions in the brain of V1, V2, V4, and IT, then it's pretty difficult to even assign anatomically which layer corresponds to which region. So the first problem is that this mapping to anatomy is pretty difficult. And then a second problem that neuroscientists tend to get hung up on is that there are no temporal responses in these networks. Like we know that the visual cortex is highly temporal. It's not just one pass and then everything is silent. There's constant activity. Images are processed in multiple loops, and all these feed-forward models have a very clear lack of these temporal processing steps. So our idea was that when you look at the weight blocks in these networks, then typically what you find is that there is a certain block design based on specific convolutional filters or kernel sizes rather. And then there's many instances of this one block. And then there's a different block design, maybe now a smaller receptive field size or kernel size. And then you again have multiple different weights for many of these blocks. So our idea was, could we not somehow pack all of these weights into one block and sort of do away with many of these layers? And the solution to then virtually get more processing steps again, virtually get more depth, is to use recurrence. So that you can use the same weights over and over, but critically, it's the same set of weights. It's not different weights. It's the same set of weights that is applied. So the solution to get virtual depth again is to use recurrence, and that is exactly the model that we built. So CORnet-S is a model that follows exactly this idea, where there's very few layers, and all the areas in the model are pre-committed to anatomy. So there's a V1 stage, a V2 stage, and so forth. And then one of these stages consists of a couple of layers, and critically, there's only very few layers, but still there's this recurrent processing stream, so that the same weights, the same layers can be reused multiple times. So this together makes for a pretty compact network. And ideally, we wouldn't just want a compact network, but we'd also want the network to perform well. So that is what we tested here. So this is plotting different brain scores of this network against other comparable models. And we do find that despite being a very shallow model, CORnet-S is actually one of the top models on BrainScore. And putting this in a different perspective of plotting the model depth on the x-axis on a log scale. So here, for us, lower is better because we have fewer processing steps or fewer layers. So the left would be ideal. And then on the y-axis is the BrainScore. So here, higher is better. So ideally, we would want to be in this top left corner where we have very few layers, but a high BrainScore. And CORnet-S definitely makes some strides towards that by being much more high performing than comparably shallow models. And especially compared to the deeper models, it does not lose too much in terms of its BrainScore. And we find a similar thing for ImageNet, where also, again, especially compared to other shallow models, CORnet-S really has a very beneficial trade-off of top 1 accuracy and the model depth. And finally, we tested also how well does it generalize, and there we see that it might even generalize a bit better than comparable networks. So really overall, the message is that CORnet-S is very shallow. So it's in this nice sweet spot at the top left with still high performance. Yeah, there's also a stronger test of recurrence that I think I'm gonna skip over a little bit in the interest of time, but to briefly mention it, when the brain processes images, it does so, like I said, not just in a feed-forward manner, but it takes different amounts of time to solve different images. So for instance, the blue ones here are solved more quickly than the red ones with time on the x-axis. And you can test for the similar kind of behavior in CORnet-S. And again, skipping some of the details, we do find that to a first extent, CORnet-S actually predicts the temporal dynamics that we observe in the inferotemporal cortex in IT primate ventral stream. So in other words, when the brain's IT is quick to process images, and CORnet-S is also quick in solving these images. And when images are more difficult, then the brain takes longer, and analogously, CORnet-S also takes longer to solve these related images. Yeah, and this is again the hammer against all of the default models, which just cannot predict neural responses over time. Yeah, so wrapping up the CORnet-S part, this is a more shallow model than comparable models. It maintains high performance through this virtue of having recurrent processing. So even though it has way fewer layers, it still regains the virtual depth by applying the same set of weights over and over. And finally predicts, or is the first model to predict the temporal dynamics in the brain's ventral stream. Okay, so the overarching message and approach that I and our lab have taken is that we try to set up this loop, and I think Thiago showed this before too, where we compare models to the brain, and the platform that we're building for this is BrainScore. And then we build more brain-aligned models such as CORnet-S, and all of this is an iterative process where we constantly try to break the models and improve the models, break them again, and so forth. I do want to point out all of this code is on GitHub, so you can access all of this for free. And BrainScore is also a website I would encourage you to visit. And to focus a bit more on this workshop again, I wanted to, highlight that the work that Thiago presented earlier and one I presented right now has actually been combined in a model called VOneCornet. So they use a VOneBlock frontend combined with the CORnet-S network as a backend network. And that is actually one of the best models now on BrainScore if you want to check that out. And again, I've put references to papers as well as the code here. So all of this is freely available, and you can use this. And maybe to give you some ideas of how you might want to use this, I thought about some of the projects, and I think there's actually some pretty nice synergies here, both in the limited time we have, but maybe also more long term. So one idea that has been floating around for us, forever now, is that you could try to integrate VOneCornet with Luigi or with a hardware chip design. And because CORnet has way fewer layers, you might actually get some good trade-offs in terms of hardware efficiency. Because you have to pack less steps into the hardware, you might become more efficient. Another idea, we've talked about this. You could try DVS input for all of this to adapt the VOneCornet on the V2E. This might lead to more robustness, more efficiency. Maybe it's also going to be more brain-like. If you build models that especially large-scale models that are trained on ImageNet or something comparable, I would encourage you to test it on BrainScore. We can very easily tell you how brain-like it is. And finally, you might want to use this kind of model as just a generic feature encoder as a vision front end for an RL agent that you then test downstream. Yeah, I'll leave this slide up. Happy to take any questions, and thanks for your attention.
Hi, Emery here. I have one quick question. So what is BrainScore? So what are the criteria? Is this like a correlation or like representational similarity analysis?
So right now, the main metrics that we use is neural predictivity, where you fit a linear regression and test it on hell of data, which then is being correlated. But we are actively adding other kind of metrics. So I guess the big picture idea of BrainScore is bring data and models together in whatever metrics and benchmarks you see fit. So it's not limited to one or the other. The main limitations are it has to have some visual input and should be part of the ventral stream. And ideally should perform some of the behaviors that like object recognition. But there's many different ways of comparing real data and model activations. So we also have RDMs for representational similarities. We're experimenting with CKA from Komplet et al. So it's not limited to one or the other. It's really a platform that's trying to host sort of our field's collective data as quantitative benchmarks to guide the models to becoming more brain-like.
And when you say, maybe a quick question then. When you say neural data, are you referring to spike counts or local field potentials, or what is the?
Right. Yeah, that's something we haven't super clearly defined right now. It's what we have right now is primarily spiking data, but the idea is that as long as you can run the same experiment on the model as you've run on the monkey or human, then it's all fair game. So if you have local field potential data and you can run something similar on the model, like you show the same images, and then you tell the model, oh, I want to record local field potentials now, then ideally the model can somehow deal with that. And like that's not on you as the data or benchmark submitter, it's on the modelers. So it's not limited to a particular data either. Just, I guess, for practical reasons, right now we're mainly working with spike data because our lab collects that and most of our close collaborators collect that. But I think Camilla Jotzwik is experimenting with EEG data right now from, I think, humans. There's also been some ideas around using fMRI. Yeah, LFP is something we've talked about, but don't have data for right now. So if any of you have data that you think might be a good fit, then yeah, please get in touch.
So a quick follow-up on that then is, so in the results that you showed with all these points on brain score, that was using the primate data, which was multi-electrode arrays, I guess.
Let me try to get back to you. So you mean, for instance, like this plot, for instance, yeah. Right, yeah, so these benchmarks, yeah, this is from the 2019 paper. So this was all primate specking data, yes.
But the behavior is human psychophysical performance.
That's right, yeah.
I also want to ask a question. Is there a correlation between the brain score and the classification accuracy, for example? Sorry if you have already mentioned and I missed. So yeah, basically, can we say that if the model has a higher brain score, then it performs better?
Yeah, that is one of the correlations we find. So yeah, like generally, if models are better on like here ImageNet performance, then they also tend to be better brain score. Although one interesting thing that we're finding recently, last 1 or 2 years only, is that the very latest models from the computer vision community that further improve on ImageNet actually tend to fall off a bit, or like they will be sort of down here. So maybe that's a sign of over-optimizing on ImageNet, but we certainly find that they do not seem to be better models of the brain. Maybe one other interesting data point, since they've been all the hype recently, these vision transformers, they also perform better on ImageNet, but they really, really fall off. So they do not seem to be very brain-like under our measures at all. Although they behaviorally, I think they're okay, but if you look at their internal neural processing, then they do not seem to match the data under consideration here at all.
Thank you.
I know you touched on it only briefly, but I was interested in the dynamics that you showed. Can you go back to the slide where you correlated, I think, the time it takes for behavioral experiment? Yeah, exactly. So this object solution times on the x-axis, is that given by somehow the number of passes you have to do in the recurrent path, or how is that defined?
For the model, yes. For the monkey, what is being done is recordings of IT at different time bins. So I think this was 10 millisecond time bins, and then at every millisecond time bin or 10 millisecond time bin, you ask, can I already solve the image from the representations that I right now have in IT? And there's different accuracies. So this is the y-axis here, and at some point you hit the accuracy that is basically the ceiling that you get from behavior. So IT is at some point as good as behavior. And that is when we call it, this is now the object solution time. So now the object is solved in IT. And that's the time step that we then try to get in the model as well. And yeah, for the model, it's just recurrent steps that define basically the same analysis. So different recurrent steps in the model. We test, can we already solve the image from the current representations to the behavioral threshold? And if yes, then that is the solution time, and we correlate the model solution times with the brain solution times. And yeah, that is exactly the plot you see over here.
One more question from my side. So the motivation for designing this CORnet architecture was because of the difficulty of mapping from the many layers of ResNet, for instance, to the layers we observe in Cortex. Right. But, I didn't quite understand how then do you obtain the brain score when you for ResNet, not for CORnet? Is this with this linear mapping? That
so basically what we do is so if this animation, so we have separate sets of public data that we test all layers on by default. So when someone submits a model, they can either pre-specify which layers they would want to be considered for V4, for instance, or if they don't do that, then we sort of help them. We help the machine learning models to become brain models. And yeah, what we do there is we test every layer in the model on separate public data, and then we choose the, for instance, best matching layer for IT or for V4. And then that layer is locked down. So for every private evaluation that we then do and everything that is shown on the website, this layer is locked down and cannot be changed anymore. And that is then being tested on everything else. But it's a search process that is first done on separate data, but just really just to help modelers. For CORnet-S, for instance, this does not happen because everything is pre-committed. So CORnet-S has this pre-anatomical mapping, which blocks correspond to which cortical regions in the brain.
Thank you.
Yeah, and I think it's important to emphasize that maybe going forward, the public data is public, and so modelers can use it to choose their own model V1, V2, V4 using whatever approaches they want with that data or other data. And then when they commit the model, they already commit the model with pre-committed layers. So like for V1 scores, only look at this layer. For V2 scores, only look at that layer. So for example, for the VOneNet, we could also have, not specify that the VOneBlock was the V1, but that didn't make sense because the VOneBlock was designed to be a model of V1. So the V1, for example, V1 ResNet 50 is kind of like an hybrid model because it has a pre-committed V1, but it doesn't have a pre-committed V2, V4, and IT. But then the V1 CORnet-S has all of the layers pre-committed.
And maybe it's also worth mentioning, like this pre-mapping probably sounds like a small deal to the engineering crowd, but if you try to experiment on these models from a neuroscience perspective, you can try to figure out what happens to V4 under certain changes. And having this pre-commitment is really a massive help because you don't have to think about all these possible combinations anymore. You basically work with a lockdown model, and that just conceptually makes it much more easier.
Great. Any more questions for Martin?
Hi. You showed this iterative procedure, how you improve your CORnet models to improve on the brain scores. Is this done by human labor or some auto optimization loop, or exactly this slide?
Great question. So right now, we ideally we would want this whole cycle to run as quickly as possible, and that's I think a big aspect of what like Jim's lab is trying to build. So BrainScore is basically optimizing the top part of you can automatically evaluate models on data without having to worry about it too much. And then the bottom part of building more brain-aligned models, we would love to optimize this, and there are some ideas in like architecture search, automated architecture search, as well as training models on separate data itself. But this is really strongly human in the loop right now, and I think we're not yet clear on how we can get the human out of this loop as much as possible. I guess the best approaches are things like architecture search, and other ideas for machine learning that try to automate this entire process in their world. But we're trying to do something similar here. Right now it's manual. So it's really more of the creative process, I guess.
Okay, thanks. And one more question. I also already asked this to Tiago, but maybe you also have a comment on that. So from my knowledge, current artificial models tend to focus a lot on texture, whereas humans focus a lot on shape. And have you done some kind of analysis to match this to BrainScore, or is there some correlation between focus on shape or texture? And
so I think the original authors of people like Robert Garros, I think they did some analysis of trying to correlate sort of the shapeness of network to BrainScore. I think they didn't find any clear correlation with most of the measures we had. The one they had was, I believe, with behavioral match. So if you make as a model, if you make the same mistakes as a human, that was the behavior benchmark I showed before, then you also, I guess, tend to use shape over texture. But other than that, I think that we haven't yet identified a clear correlate of that. I think Tiago is working on that a little bit, and we're also talking to Robert and the Bethke group to trying to figure out if there's something that can be done about identifying sort of the neural substrate of what is going on there. But I don't think we have a clear answer right now.
Thanks.
There's also a question from Sami in the chat, if you'd like to answer that.
Oh, can you read that? I have one monitor right now.
He says, or Sami, if you're there, you can also go ahead.
Yeah, hello. Okay, so my question was, so it's to see if I understood well. So if we enroll the recurrent connection of our CORnet-S network, it's like repeating the same convolutional block multiple times with share weights. So when we talk about shallow networks, it means a few parameters, but the network is very deep.
No, so you said like, how do we define shallow networks? So here, shallow is defined as having fewer layers. So if we go back to the architecture, then let me just go back to the idea. So instead of having many weight layers, like a shallow network would only have few weight layers, but then you repeat the same weights, like you said, the same convolution operator multiple times to virtually get the depth back. But in terms of model architecture, it's really way fewer layers.
Okay. I see. Okay, thank you. And I had another question, but it's more related to devious inputs. Do you think it will be the brain score and so forth? Do you think it will be the same for a V1net or a CORnet-S network if we train it on devious inputs? Because the inputs are quite different.
Right. I honestly have no idea.
Okay.
and I think it could go either way. I think, that's probably, I guess, what makes it an interesting question.
Great. And then I'll stop recording and we'll switch over to our work group discussion meeting in the same room, but we'll discuss the projects then. Big thanks again to Martin for a great talk today.